Hi everybody. We have been spending a lot of time talking about derivatives. So today we're going to discuss what does it mean for a derivative to exist. And we call that differentiability. It's really how can we tell a derivative can exist. So we say it's the ability for a derivative to exist. So here's our definition. We say a function is differentiable at some x value if the derivative exists. And that's really simply what it is. If the derivative exists, we say a function is differentiable. For the derivative to exist, the graph must have what we call local linearity. So a lot of times people ask, well, what do we mean by the phrase local linearity? In other words, we're looking to see if the slope at some point, the slope from the right equals the slope from the left. So we say that the left-hand derivative equals the right-hand derivative. Graphically, this is what it would look like. Let's say I wanted to graph the function y equals x squared. Let's say, so we're going to graph the function y equals x squared here. So x squared. If I were to graph that, whoops, hit enter. There we go. We get our parabola. And let's say I just want to zoom in. And I'm going to pick some x value right here, over here, right here. There we go. If I keep zooming in at this point, if you notice, the more I zoom in, the straighter it's going to look. And the more we zoom in, of course, it looks straighter and straighter. So what we mean by local linearity is that if I pick this point here, let's say, does the slope coming into that point, does that look like the same as it's going out at that point? And the answer here is yes. So we say, sometimes we just say it's slope in equals slope out. That's easy to see on a parabola. But let's see if we try this absolute value of x. So let me go ahead and clear this out. But now let's graph the absolute value of x. Absolute value of x. If I hit enter, there it is. Now watch what happens when I zoom in. Whoops, when I zoom in at the origin. Notice, last time with the parabola, as we kept zooming in, it made it look like it was getting straighter. But here, it always seems to stay the same. It never changes. It's always formed that little sharp corner. But if we notice at this point, whoops, escape. If we notice at this point, here we have the slope going in, and here we have the slope going out. Clearly, they aren't the same. So we say that this does not have local linearity. So we say it's not going to be differentiable. And therefore, we cannot find the derivative of this. So to determine if a function is differentiable, we're going to talk about the following no-nos. So we're going to say this. A function is not differentiable if, one, if the function has a sharp turn, like absolute value. If we look here beforehand, the slope is going to be -1, and immediately afterwards, the slope is going to be +1. So we say at that corner where those two slopes meet, we cannot have a derivative. So we say no corners. In other words, we say this must be what we call a smooth function, like butter, like a criminal undercover. Now the other point that we have is, well, what if the value does not exist, like at an asymptote? And in this case, that should be a square there. So the other one says, if it has any discontinuities. So that talks about continuousness. So we say that the function must be continuous. What does that mean? Well, obviously, no vertical asymptotes, no holes, and no jumps. Very simple to do. The most confusing one is this one. This is our vertical tangent. We know that a horizontal line has a slope of 0, but a vertical line in pre-cal, we would say that slope is undefined. Well, there's a reason that slope is undefined. It does not exist. So at a vertical tangent, the slope does not exist. Or I guess the slope just does not exist. And therefore we say, because the slope does not exist, we're going to say it's not differentiable. So differentiable really just means the same thing as the derivative, as the slope. We use them synonymously all the time in calculus. Instead of saying slope, a lot of times we just say it's not differentiable. In other words, the slope does not exist at that point. Another one is at a cusp. Now let's take a look here. Let's see if we could graph this derivative right here. We're going to do this later on today anyway. So as we approach 1, if this is my derivative graph, as we approach 1, notice the slope is negative. And as we get closer and closer to 1, it becomes more negative. So it's a negative slope. So above here we have a positive slope, and below we have a negative slope. So as we get closer to 1, the slope is going to get smaller and smaller and smaller and smaller, like so. It becomes asymptotic even. As we approach 1 from the right, notice the slope is positive. Well, but it's getting steeper and steeper. Well, what's going on? This is going to get steeper and steeper, like so. So if we notice, at this point, on one side the slope becomes infinitely small, and the other side it becomes infinitely large. So we have a special name for something like this. This is called a cusp. In other words, it's kind of like a corner. Matter of fact, we call it a corner. We're okay with that. But it's called a cusp because the slopes go to infinity. So at this point, what we say is that the slope is approaching infinity. So if there's a cusp, again, not differentiable. So let's take a look at an example here real quick. Down here where it asks us to list the x values for which the function appears to be not continuous and not differentiable. Now, so let's talk real quickly here. The derivative will not exist at an endpoint. Now, this is very important for us. So let's go back up when we talked about differentiability, right? That is that idea of that local linearity. Notice we're talking about the slope from the left equaling the slope from the right. Well, at an endpoint, we say the derivative cannot exist because there is, like at this endpoint right here, there is no slope to the left. Over here, there is no slope to the right. So therefore, at endpoints, we always say that the function is not differentiable. So let's answer question A. Where is this not continuous? Well, we do consider continuity at endpoints. We saw that in the previous video. But this is not going to be continuous at x equals, looks like 6. So x can't be 6. And the reason for that? Well, the limit just does not exist. I don't think there's any other ones. So now let's talk about differentiability. Well, we just got through saying we can't have an endpoint. So 0 and 10 cannot be. The reason why? Those are endpoints. Next, it looks like at 3 that there is a corner here. So x can't be 3 because it looks like there's a corner. Likewise, at x equals 8, x can't be 8 because that's our cusp. Now again, if you call that a corner, we're going to be okay with that. We're not going to come at you. Now, at 4, it's kind of hard to see, but at 4, it looks like there's a vertical tangent. So it's not going to be at 4 as well. Some people do say at 5, I guess that could be considered a corner. It was supposed to be smooth, but it looks like a corner. That's okay. We don't worry about ambiguity here. So very easy to do these. So let's now take a look at our next example here. So for here, it just asks us, describe the x value for which x is differentiable and points where f is not differentiable. So what we're looking for here, what values will the derivative exist here? It's better to answer the first one. So it's not differentiable at 2. So x cannot be 2. And the reason for that, again, there's a corner there. So where is it differentiable? So we can say f of x, we can write it this way, f of x is differentiable on the domain negative infinity to negative 2, soft brackets, excuse me, or from negative 2 to infinity. And there we go. So what about number 2? Well, easy. X can't be, it looks like, I guess that's a 1 there. Can't be 1 because that's a vertical tangent. And where is differential? F of x is differentiable on the following domain. Whoop, should spell out differentiable on the domain negative infinity, soft bracket again, keep doing that today, to 1, or 1 to infinity and beyond. Number 3, looks like there is a vertical tangent at, looks like negative 2 there. So x cannot be negative 2. Vertical asymptote, sorry. It's a vertical asymptote right there. So we would say this is differentiable. F of x is differentiable on the domain. Yeah, look, I did soft bracket. Negative infinity to negative 2, or from negative 2 to infinity and beyond. Super easy to do. All right. Now the next one's pretty easy. At which point is the slope to the graph of the graph 0, positive, or negative? 0 is easy. That's where we have these horizontal slopes. We talked about that the other day when we did our power rule. Remember where the slope is 0. And that looks to be at B and E. Positive, C and D. Where's the slope positive? Not the value, but the slope. Where is this negative? It looks like A. A lot of people say, well, what about F? Well, F is an endpoint. Remember, we can't have an endpoint. So therefore, it's not differentiable. Remember, when we say differentiable, just think derivative. I say differentiable, you say derivative. It's very simple. Ready? Let's try it. Differentiable. Good job. All right. So go to the next video, and we'll take a look at a couple more examples. I'll see you then.